he's speaking. Good. Okay, so Java 8 functions. We started to talk about these last time. What are functions in Java 8? Why am I talking about this? What are these functions? Why do we care about functions in Java 8? Well, Java 8 introduces a broad set of functional language elements, things that help you do functional programming more effectively and capture functional abstraction. They allow you to wrap things up in a function, including creation of closures, as we'll see. And in traditional Java, when we wanted to capture different functionality in a parameterized way, different rules passed in, what we would use was indeed we would go and we would use for example, an interface and implement a method of it in different subclasses in different ways. So here's the compute liveness rule. This is in classic Java, right? Compute liveness rule, and we go and we have this rule that we figure out, and we pass it down through successive levels: update space, updates or run scenario, update space, update cell, and then we apply this rule to execute the rule that's desired for Conway's game of life. And in order to parameterize those rules, we have down here. Here we go. There we are. This is how we create the mapping for different rules. Could someone get the left button back there? It's kind of washed out. The screen is not pink, hopefully. Okay, so here we define a mapping in the form of a hash table. It's a dictionary of sorts, where we map between a command line argument, where we select the rule, and the rule. Now, when I say this encodes the rule, this new compute liveness classic, or new compute liveness remain alive 2 through 4. How does this capture the rule? Anyone? What's going on here when I say new compute liveness classic? What am I doing? I'm allocating an instance of a what? This is not a trick question. Begins with a C, ends with 2 S's. An instance of a class. Good. And why is it that do I say that encodes a rule? Well, let's go see. Compute liveness classic is going to implement this compute liveness rules, including a method called apply. Okay, and let's go find where that is defined here. Here it is. Here's this static class. It implements compute liveness rule. Static because I'm not depending on the value of this in the overall class. And here's my method apply. And apply here encodes a rule. If I have a certain, if I'm alive or not as a cell, and I have a certain number of surrounding cells that are alive, I do something depending on the values of that. So if the current cell is alive, I'll do this. Otherwise, in other words, if the current cell is alive, the current cell being considered, the question is, does it survive? Only if the numbers around us are between 2 and 3. If the current cell is empty, does it get colonized? Only if the numbers around us are 3. That's our apply. That's our rule there. And then we have other rules. And each of these rules is encoded in a class. Encoded in a class. Okay? Now, I could have avoided naming these and just used anonymous classes and just kind of filled these in. But I thought it'd be a little bit cleaner to do like this. Okay? So each of these classes encodes a rule. They each implement this interface here, and then we use them to parameterize that rule for these lower level things. We pass it down, run scenario, run update space, update cell, and then we apply the rule here. Classic Java. Now, with Java 8, we don't have to do that. We can actually encode rules as functions. We can have functions being passed around, much as we did in Python, much as we do in Racket or Clojure. Excuse me, what am I doing? This Clojure. Sorry. in the language Clojure or Scala, we can pass around these functions as first-class things. Okay, and I noted last time that Java's type system has been expanded to incorporate these things, and I tried to help you make sense of this cacophony. By functions and suppliers and consumers and predicates and operators. It's a bit of a mouthful. It's a bit of to sort of come to terms with it. But fundamentally, there's a method to the madness, and there's a set of clear meanings about what's meant by an operator compared to a function, compared to a supplier, consumer, and predicate. Okay? So we talked about this last time, and I noted that you could create these functions in many ways. Here's 3, for example, functions being created. Here are functions being created. Here's an int binary operator. It's an operator because it takes in values that are the same type as it returns. It operates upon the values. By contrast, we could take in a function. We could define a function that takes in values of one type and returns another. Okay. And I noticed these functions could come from many sources, and we could define them, through lambda expressions, these things here, or we could pass in references to methods in a class, for example. Okay, now I stopped last time at this point where I talked about closures. Okay. And a closure is basically associated with a function with some environment to which it's evaluated. It knows the values of certain free variables that it needs to remember in order to do its job. Okay? Variables defined outside of the function. So you have this function, and it's being used, but it has references to certain things outside of it that it needs to retain values for. And it turns out that in functional languages, and languages supporting functional capabilities, including JavaScript, and including Clojure, and including Scala, and including Groovy, and including Java 8, we have ways of doing this with restrictions in Java 8. Okay? So if you return a function, it needs to remember certain values outside of itself on which it depends. Okay? And it turns out that there's some rules in Java that are not that restrict how you can use these things. Okay, so I'd like to talk about these things. So imagine if we have A calling B. So we have A, it calls off to B, and then it returns to A. Okay, we're going to have this kind of sequence here. And in order to capture that, we're going to have a call stack, right? So I drew the call stack over there. One function calls another. We're going to put things on the call stack for each successive call and pop them off when we return. Okay, and the call stack keeps track of where we were before we made the call, and it keeps track of all the data associated with that context. So when we come back, we still have access to our variables and so on. Are we comfortable with this notation, the call stack? You've seen it in 2.4.15, right? People took 2.4.15 way back in the day, and you saw call stacks? Yeah? Where else did you talk about call stacks? Anywhere else? Any other classes? Sorry?
332.
332, good, yeah. 332 they'd figure. Probably compilers, if anyone is in compilers right now. Okay, not too much. Maybe Encode phase in the next few weeks. Okay, so here, ladies and gentlemen, we have 3 functions. Foo, bar, and, okay, I lapsed, okay? There's no baz, there's a create increment by. Okay, so here we have foo, and foo and bar are both methods. Okay? Foo calls off to bar, calling this dot bar, and bar basically does some computation to create x, a value x. It figures out an integer value x, and basically it calls off to create increment by with this value x, which is an integer. Okay? It calls off to this, and this create increment by returns a function. Okay? It returns a function that takes in an integer and adds x to it. Are we okay with that? That's what's going on. Foo calls bar. Bar calls create increment by to get a function back. And bar itself returns the incrementer it gets back. So here's the incrementer. If x is 1 here, what does this incrementer do that it gets back? What does it do? If x is 1, what does this thing do? If I call create increment by with a value of 1, what does it return?
It just returns 1 greater than what you pass in.
Yeah, it returns an increment function, a function that, given an argument, returns 1 greater than the argument. If x is 10, what does create increment by do? It returns a function that does what in life? It takes a value and
Returns that value
plus 10. Yeah. Okay, good. Okay, so here we have create increment by creating function. Now, a key thing here, folks, is that this function that's being returned, it's given y. When it's called, this function being returned by create increment by, it's going to be given y, right? It's a function from y to something else. So it's going to be told what y is. This incrementer is going to be called with a certain number. And its job in life is going to be add 10 to it, say. So it's called with a certain number, and it's going to need to add 10 to it, or need 1 to it. In order to figure out how to do its job, it needs to remember something besides y. What is the other thing it needs to remember? X. It needs to remember x. It needs to remember what x is. So if you call create increment by with 10, you get back a function that knows its job in life is to add 10 to things that are given to it. If you call create increment by with 1 as the argument, it needs to remember that its job in life is to add 1. In short, it has to remember what x is for it. For it itself. Does that make sense? This has to remember what x is to do its job. Okay. Okay. Forgive me. I'm going to plug this in, or else bad things may happen. Okay. Okay. There we go. And we're going to get this. Okay, great. Okay, so create increment by, the thing that is returned by create increment by, the function, is actually more than a function. It's a closure. It's a function. Adds things, adds x and y. But it needs to be paired up with some memory of what x is. Not just a function by itself. It's a function that has to remember something. Does that make sense? Okay, now, all these things we were talking about before, or some of them with the call stack, plus these factoids combine to yield the restrictions in Java 8 concerning how you can use anonymous functions and closures, or use functions and closures. So here we have foo calling bar, calling create increment by. And we're going to imagine the call stack associated with this. So here we have foo down at the bottom, and it calls bar. And bar calls create increment by. And when foo calls bar, it calls it by this dot bar. And so this actually refers to the same object in memory for both of them. This dot foo is calling this dot bar, and they're both referring to some object. This is something. The current object is a certain object in memory, a certain instance of a class. Now, bar has a variable called x, right? Bar has this variable called x, which happens to share the same name as this one, but that's totally irrelevant. These are two different values. I hope you understand that, right? From this, just going back to basics here. Even though this is called x, this might as well be called z, because it doesn't in any way interfere with this x. There's no relationship here. This x here, being in the function returned by create increment by, is returning to this, but is referring to this x, right? It doesn't care whether this one is called x or called z. It doesn't care in the world. So these are two different x's, the one up here and the one down here. There. And the reason they are two different ones, they can be kept track of separately, is in part because they live on different stack frames. There's an X up here which lives in this stack frame, and there's an X down here which lives in this one. So this X is remembered after the, while this one is being executed, so when we return, it goes back to that. Okay, so that's some basics, but I'd like to reflect on what's going on here, ladies and gentlemen. Let's consider the fact that when we return from create increment by, what happens to its activation record? What happens to its stack frame? What happens, in short, ladies and gentlemen, to this guy here? When create increment by disappears, what happens to the green thing at the top? When create increment by disappears, in other words, when it returns this function here, this closure, what happens to the green activation record? What happens to it? Gets popped off. This disappears. It's deallocated. Allocated in the sense that it just leaves it and it's ready to be overwritten. It can be overwritten after that with a call to something else. Maybe bar calls Baz, and it will overwrite this activation record that's there. Basically, it clears out of that, and it doesn't use it anymore. It's freed up for later use, right? In no way does it depend on it. So you'll notice what's here is X. That in that green record was X, and this thing that we're returning depends on X, right? This depends on X. And yet, that activation record is disappearing. How is it going to remember this X how is it going to remember what this X is if the activation record that stores it disappears when it pops? Right? So foo calls bar, this activation record for bar is put on. Bar calls create increment by, this is put on. Create increment by returns, this one will go away. For all intents and purposes, the green is wiped out of existence. Sadyala. And when bar returns, this is wiped out of existence. Boom, gone. Right? You folks don't seem as excited about it as I do. This is wiped out of existence, right? When create increment by returns, this green guy is gone. So how is it going to get the value for X? That's the question. Okay, so if this guy disappears and this guy is counting on the value of X, how is it going to remember it? Well, in general, ladies and gentlemen, it's only going to be able to remember it if it's a constant. It's not going to be able to remember it if X, it's not like X can continue to be fraud, to be manipulated, to be written to. It can only take this value in if it's a constant, if it knows how to remember that constant, okay? So Java 8 will be perfectly happy with this. Why? Because the value of X does not change after we return it in any way. So it'll just remember whatever value it was here, it will remember it. But if you have something like this, where you have a function you want to return, and after you create that function, you go and you try to fraud, but you try to change this value of X that it's depending on, it will be bitterly unhappy. Java 8 will balk. Java 8 will give you an error message. It will say that's not a final value of the variable. In other words, X isn't constant anymore. It's not just 3 or 10 or 1 like it was before. Instead, you're going and you're modifying it. And that could cause problems, because when it creates this closure, when it creates this function, it needs to remember things. It needs to kind of freeze the value of X that it's depending on. And if you later try to change it, it will be mightily unhappy. Okay? The compiler won't let you do this. As a result, X needs to just hold the value of a constant. Okay? And Java will enforce that. Java will enforce that. It will prevent you from doing this, from modifying X, because it's already counting on the value of X. And now you're telling it, well, X has changed. go update your knowledge of it, and it can't do that. It needs to only depend on constants, so when this guy returns, when the green guy here returns, it's not counting on what's in X anymore. So when it creates that function in Java 8, it's only taking a snapshot of final values, that is, values that are constant, using the final keyword, for example, or implicitly constant because they're not overwritten. So X might depend on values that are constant, but if you try to give it values that aren't constant to depend on, like X here, it won't let you compile. Okay, now let's talk about something else. Okay, ladies and gentlemen, so this thing would disappear. We want to just remember a value. Okay, now let's go to another case, which is subtle. I'm trying to get onto this issue of what Java 8 supports. Now we have foo and bar, just like before. But now, ladies and gentlemen, we have create increment by, which is no longer static. Instead, it's a regular method. It's not a static method. Instead, because it's not a static method, it depends on this. It has access to this, right? A static method doesn't care what the value of this is. It's a function independent of the value of this. Here, it cares about this. So I could have written it explicitly. In fact, that probably would be a good thing to do, for me to just write this very explicitly. And I should to adhere to naming conventions, I should probably say this. This dot create increment by. Okay. So now this is not static. This is in fact an instance method. Okay. And you'll notice that I say this dot x here, and then I can say this plus plus. And it turns out that's not a problem. It was a problem to say this, to say, what you see here. This is not a problem. Yes, that's true. What you see here is not a problem. And it turns out it's because Java 8 deals with this by remembering the value of this. Okay, x changes, yes, but x is an instance variable of some object in memory. Here we have some object in memory, and this refers to this object in memory. Refers to the blue object up there at the top. Okay, and this object in memory will outlast the green activation record. Before, our x depended on that it lived in this green area. So when we popped this off the stack, x wasn't going to be around anymore. So we couldn't count on the value of x in this sort of way. Okay? Oh, wow. I have no clue what that is. Should I answer it? Okay. Has the phone been on a motorized vehicle in the past hour? No. Thank you very much. Okay. I don't know. In any case, I could have told it about x, right? Here, each of these guys is referring to a variable in memory. This refers to that. And that instance of memory doesn't disappear when this top guy disappears, right? Before, we had this top activation record holding the value of this. And that was a problem if x was going to be changing. So we basically said, instead of just continuing to use x after it gets returned from this activation record, we just are going to only allow for constant x's to be used, in which case we're not going to allow for x to be changed after we've depended on this, because this activation record will be disappearing. So we only allow for dependence on local variables or parameters which are constant, which don't change. This is why this is an error. It's because it changed. This is fine because x, once given, never changes. So it allows us to do this in Java 8, but not this. Not the one you see here. For what you see here, it's fine because this .x continues to exist after this activation record is popped. Do you see that? This activation record can go away, but, excuse me, this one here. This activation record, the green one, can go away, but x still exists, right? This .x still exists. It doesn't end its life with this green record. Hence, in Java 8, we are allowed to do this. We are allowed to do what shows what it's standing before you. We're allowed to say this .x because this doesn't disappear with that activation record here. It doesn't go away. We're not counting on something that being able to keep track of changes to something which is going to disappear. Hence, ladies and gentlemen, we can depend on x on an ongoing basis. We can return a function that depends on this .x, and it will continue. This function will remember this. It will remember a reference to this blue object with x in it and continue to use it. And this x may evolve over time. Think about that. If that doesn't get you excited, I don't know what will. Think about that. We have a function whose job in life is not just to add 10 to everything that's given, not just to add 1 to everything that's given. Its job in life, ladies and gentlemen, is to add whatever is currently in this .x to whatever is given. Or maybe this .x evolves over time in some sort of way. And it'll be adding whatever is in this .x to whatever we have. Java 8 is perfectly fine with this. So closures in Java 8, if they depend on a local variable, or a parameter like this, like what you see here, it can only be in the context of a constant value, a value that's explicitly final or implicitly final. It doesn't change. By contrast, ladies and gentlemen, it can depend on an instance variable that is changing over time because that instance does not disappear with the activation record. It doesn't go away with it. Does that make sense? Because it's not depending on something fragile. It's not depending on something it won't have access to after it. If it's depending on something in an activation record, this guy, it's horrible. If we're depending on the activation record, this activation record will disappear. We can't continue to depend on this memory to keep the value of x. So it has to be constant. Here we can continue to depend on this. Okay, so we're a happy camper. Okay, so ladies and gentlemen, that is the story, or perhaps I should say this is the story of Java 8 closures. There's subtleties associated with this, but if you understand this general rule, you can't depend on a non-constant parameter or local variable. By local variable, I mean, something that, for example, like this guy down here in the blue, so a local variable like int x equals this. You can't depend on a parameter or a local variable, a parameter or a local variable that's going to be changing. They have to be constant, but you can depend on an instance variable because that instance is not going to disappear. It's going to outlive it will live as long as needed. The garbage collector will let it live as long as it's referred to in the function being returned. Okay? Okay, good. Because that's a kind of natural nugget here, I am actually going to try to stop this. Oh man. Okay.